the last video what we had discussed was a looping algorithm for a 4 by 4 or 8 by 8 in general for the Bayes network, and we were able to actually generate mapping from any input to any output combinations. Any kind of map we take, we were able to set up the connections, but we have to carefully use the algorithm. If you recall, I had also shown an example that there was a blocking in one of the switch, and for the same map then I could actually do what we call again another connection diagram using looping algorithm, and all connections we were able to meet through. So, technically if there is the blocking happens, you just actually dismantle all the connections, do it again as per the looping algorithm, and you will be able to set up the connection. That is basically the rearrangeability in the switch. So, it is a rearrangeably non-blocking switch. Okay. So, what we will do is now we will actually generalize this notion of rearrangeably non-blocking, and we would like to understand in the closed network under what conditions a closed network becomes a rearrangeably non-blocking. So, this is essentially is being known as Slepend-Witt theorem. This is again for unicasting. We can actually do a similar exercise for multicasting also. Okay. So, at some point of time, if time permits, I will probably will also introduce the equivalent of Slepend-Witt theorem for a multicasting scenario. Okay. So, this theorem actually states that a 3-stage closed network is rearrangeably non-blocking if and only if. So, this is a necessary as well as a sufficient condition for rearrangeably non-blocking switch. So, I will also draw a closed network to again emphasize on what these symbols actually means. These are the same symbols which we have used earlier also. So, the R2, which is the number of switches in the second stage, is greater than equal to maximum of M1 is the number of inputs to the switches in the first stage. So, in the first stage switches are M1 by N1, okay, is under that case, and N3 stands for the number of outgoing ports in the third stage switches. So, third stage switches are M3 by N3 switches. Okay. So, this is the condition, this is the closed theorem, and we have to essentially now prove that yes, this is going to be true. Now, there is a particular case when the switch is symmetric. So, I can further add in particular a symmetric network with M2 is equal to with N1 is equal to M3 is equal to R2. Okay, this is actually happens, and another condition is M1 should be equal to N3 is equal to we define as N. So, this is a condition for symmetricity. This condition is always true for the closed network. So, in fact, I need not write this, I can actually only work with this condition. So, a symmetric network with this thing is rearrangeably non-blocking if and only if. So, this is actually symbol used for if and only if R2 is greater than or equal to n. So, in fact, this same condition degenerates to this under that scenario. Just for recollection, rearrangeably non-blocking actually means when a switch is being operated upon, you want to set up a connection and there is a free input and there is a free output port, but you are not able to set up the connection because there is no path available. But if you can actually using a mechanism, you can dismantle certain existing connections and again create them, same connections are being established again, but by doing so you are able to create a path for this the free input and free output port which you were for which you are trying to set up the connection, then switch is a rearrangeably non-blocking switch. Okay. So, let us see how we will actually prove it. So, we are looking into the closed network. So, closed network, again for reference I am just drawing it here. So, this closed network what we are talking about. So, in this case, now let us start with the proof of this one. So, there is a free input port somewhere here, this we call switch A, this we call switch B. Okay. So, this is the switch A, this is switch B, there is a free input port output port here and there is a free input port here. So, this is what we want to connect. Okay. So, when we want to establish a connection between A and B, so these are the switches. If R2 is greater than or equal to maximum of M1 and N3. So, if this condition is satisfied and we want to set up a connection between A and B have been identified there. In that case there will be two possibilities, either so this actually setting of connection equivalently in a Paul's matrix is equal to what? If I draw a Paul's matrix for this closed network, so A must be some row and B has to be some column. So, how we will put up a connection? We will actually put up some second stage switch, that entry has to be put in here. Okay. Now, I should either find out a symbol. So, these are 1, 2, they are total are 2 symbols representing the middle stage switches. So, they can be here. So, depending on A is being connected to which all middle stage switches, B is connected to middle stage switches, will decide what all middle stage switches are present here. I need to find out among in this row as well as in this column some element which is not there in row as well as in column. Okay. So, either that thing is going to happen. So, I will state that there exists a symbol not found in row A as well as column B. Or either this will be true, but sometimes this may not be true. In that case, the second condition is always going to be true. So, this either an or will be happening. We will actually prove yes, this is going to be true. So, the B condition will be that there exists a symbol C which is actually in a row, but not found in the column B, in row A, but not in column B. Also, not only this will be happening, you should also and a symbol D So, you will find a symbol C which is there in row A, but it is not in the column B. Okay. So, there is some C here, but it is not present in the column, and you will also find a symbol D which is in column B, but not found in row A. Okay. So, there is also going to be a symbol D. So, C and D, the pair will be existing. So, one of the two things should happen, either this should be true or a pair should be happening. Okay. So, let us see whether this argument is true or not. If this is true, then I will be able to identify a rearrangement mechanism. Okay. So, let us see how this will be happening. Now, of course, we do not need this, we will be coming to the example later on, that time we will draw it again. We require the pulse matrix. Now, if condition A is not true, what is the meaning of this? If condition A is not true, it means if I look at all the symbols in A, all the symbols in B, and I create a union of these symbols, union of this set, all symbols have been consumed. All R2 symbols, the middle stage switches of the closed network have been consumed, they have been put in row and column both. That is why you are not able to find out one element which is not there in row as well as in column B. Okay. So, that what must have happened, but if that is true, that number, the in fact symbols here in row A I can write as A, set of symbols in row B I can write as B, SA union SB consumes all symbols okay, is equal to all symbols but remember when I had actually drawn the A there, I had drawn a B there, there was one output which was free, there was one input which was free, which we were trying to connect. Okay. So, how many symbols could have been occupied? So, this output is being connected to 1, 2 R2 symbols. It means, and remember this R2 is greater than M1 and R2 is also greater than N1, N3. So, when R2 is greater than or equal to M1, the number of inputs which are occupied is in worst case can be M1 minus 1. You just forget this one, so remaining ones except this will be M1 minus 1, which actually implies when in row A there can be only M1 minus 1 symbols. In worst case. This is because you are having one input which is free which you are trying to connect, okay, and your R2 is greater than M1. It means there must be a symbol out of these R2 symbols which is not present in row A, but my condition says that if I take these two union of these two sets, I am consuming all R2 symbols. So, there is something which is missing here, but which is present here. Okay. So, which is going to be D. Okay, there is something which is missing here which must be present in column. So, this element we call it as D. So, D is not present in row, but it is present in column. I can take a similar logic from this side. So, maximum number of all middle stage elements which can be connected from B can be only equal to number of output channels, output ports which are occupied, which is N3 minus 1. One is this is free which you want to connect. So, which actually implies the maximum number of symbols in column B has to be N3 minus 1, but R2 is greater than maximum of these two, is greater than both of these two actually, which implies there has to be something. So, all R2 symbols are not in the column, but since union is consuming all the R2 symbols, there has to be something which is not present here, but which is present here. So, that is C. So, I will be always be able to find out a pair of symbols called C and D. Okay. So, this C and D symbols, C D pair, either I will be able to find out this because case B is true, or I will be able to find out a symbol which is not there in row as well as column. So, one of the two conditions are going to be true. Now, once these two are true, one of these two will be true, how the rearrangement is going to happen. So, let us see. So, consider this Paul's matrix. So, in case the condition 1 is true, you can find a symbol which is not in row as well as in column. I can just take that symbol and put it here. So, if that symbol is say E, I will just put it and I can use it to set up the connection from the free input port to free output port. But if condition 1 is not true, then condition 2 is going to be true. One of the two is always going to happen. So, we have just actually discussed that thing. So, if the condition 2 is true, I can always find out a C here and a D here. So, now what to do? Okay, the way the rearrangements will be happening is, I will look into the row where this D is there. Okay. So, remember there is no element which is duplicated, I am talking about a unicasting connection. Okay. Everything is unicast, there is no multicast. So, there can be element D cannot repeat anywhere, there can be only one D in this place. Okay. So, this actually means I have to now look for here some wherever if there is a C which is available. Remember C was not there, C actually can be there anywhere, C was not there in the column, C was present in this row but not in the column, and D was not in this row, so it was in the column. So, I will look for a C, if I can find a C it is fine, if I cannot find a C, so there is no C in this row, then life is simple, I can just put a C here and put a D here, connection is set up. So, this is a rearrangement. Okay, we will actually take an example for a example network, closed network, and we will try to see how we will do this. We will use Paul's matrix there to figure out the rearrangements. If you end up in finding a C, then of course you cannot put a C here because C will get duplicated. So, then what you have to do is you have to now look for a column. Now, will you ever reach and find an element here, a D here? No, you could not find a D here because D was not there in the row. So, you will exclude this in the search, you will not be looking into this row, everywhere you will be looking and you may end up in finding a D here. You can keep on doing it, you can next time look for a row, try to look for a C. Now, can you find a C here? You cannot because C was not present here in the column. Okay. You will not be able to get a C here in this particular column because C is already present. So, you will be always looking for the columns here, this and this column will be excluded, 3 of them. So, somewhere else you may get a C. So, you will this is what we call chain search, you are doing now chaining, you can keep on doing it. So, next time you want to find out a D, you cannot get a D here, you cannot get a D here, you cannot get a D here, everywhere else. Now, your search space is reducing every time. Okay. You may end up in a D somewhere and then again you will try for a C. So, you can't get C here, you can't get it here, you can't get it here, you can't get it here, or you may not get it, chain probably can end here. In worst case, what will happen is you are doing search and ultimately when all columns and all rows are exhausted, you can no more move any further and the chain will end. So, chain is going to end is guaranteed, okay, because every time when chain is being extended it is going to a new column or new row. So, once you cannot extend chain any further, you have to simply replace all D's by C and all C by D and put the D here and you are able to set up the connection. Okay. So, when we actually doing this search, this row and this column are being excluded actually, and every time you are doing one row and one column. So, in worst case, so in the beginning people thought this a very simple thing that R1 plus R2 which are the number of rows and columns minus 2. In worst case these many rearrangements will be required. Okay. In worst case these many rearrangements will be required. So, these are the rearrangements which are there and then finally you will make an entry in this place. So, this is at most maximum, but this is not the correct bound. In fact, every time you do row and search, so if the rows actually finish first, then you will no more be extending, and you can actually prove it through a very smart way. So, if the row R1 is less or R2 is less, if the all rows are finished, even if extra rows are there, you will not be travelling there. So, in fact, this should have been put to 2 minimum of R1 R2 minus 2. Okay, that would be the at most number of rearrangements which are required. This is further improved by something known as Paul's theorem. So, the Paul's theorem says, so we have actually proved the Slepen-Duguid theorem so far. Okay, now only we actually are able to prove that if R2 is greater than maximum of M1 N3, one of these conditions will be happening and I will be always be able to set up the path. Okay. And that is a good enough condition to prove it. So, Paul's theorem states that number of circuits which need to be rearranged is not this. So, number of circuits which need to be rearranged at most will be minimum of R1 R2 minus 1, it is not twice. So, this number was twice actually originally in the theorem. So, Paul's theorem actually improves on this, but what is the premise, how we actually get it? So, the idea here is very simple, I can actually describe it here. So, what we do is we take the same Paul's matrix. So, there is a and there is a corresponding element C in this case. So, how to determine the rearrangements? I said first of all find out, go across, there will be somewhere a C, fine, but I was only extending one chain. Now, let us do it alternatively. So, next time I will look for a column here, find out if there is a D somewhere. Remember, this is excluded when I am searching for D. Okay. Now, once I have got this chain, next I will look into this and find out a D somewhere. This D cannot, this is excluding this particular row because D cannot be duplicated in the row. Okay. So, I have extended, let me use colored chalks here for clarity. So, next I have extended this chain by 2 steps, now I will use this, I will do alternate chain extension. I can go like this and get C somewhere. Remember, I will not be revisiting this particular column, C is already there present, so it cannot be duplicated. C was not here and this will be excluded. And then I will again go for the next chain. So, I am looking for C, so I will be excluding this particular column, this one. I will be now looking for somewhere A here, maybe C will come here. And then of course, we will be looking for a D, you cannot come to this particular row, this row is excluded, this is excluded, this is excluded, somewhere here maybe. So, you keep on doing alternate search and every time you are extending the chain by one step. So, when all rows, so whichever is the minimum of R1 and R3, whichever is minimum of these two, that will get exhausted first, and one row and one column we are excluding in the beginning itself, they depends on, they actually corresponds to A and B. So, in worst case you will be requiring minimum of R1, R3 minus 1 rearrangements for setting up of the connection in the closed network. So, this is what the Paul's theorem is all about. Now, what happens when you are using a rearrangeable network? You are actually increasing your circuit setup complexity. In case of a strictly non-blocking switch, one step you just simply set up the path. Here in worst case, whatever is the value, minimum value of R1 and R3, those many circuits will need to be rearranged. Worst case that is possible. So, that is your circuit setup complexity, which will be roughly R1 or R3. But if switch is not heavily loaded, these number of rearrangements might be actually smaller in that case. Okay. So, let us do an example of this thing. Let me create a 3-stage network and a closed network with this same condition satisfied, and try to set up the connection to justify that this is how actually it is done, to give an example. So, let us do it. So, let us take up a network. I will take up a 3 by 3, and I am actually not I am taking asymmetric system here intentionally to give you an example, or we may actually do it for a symmetric system first and then for asymmetric. I think we can try that. So, let us take 3 by 3. So, my output side will also be 3 by 3. So, why the second is 3? Because this is N3 is 3, M1 is 3, M1 by N1. So, R2 has to be greater than or equal to M1 or N3, whichever is the maximum of the two. So, in this case that is 3. So, the middle stage will be 3 also. So, this is a 9 by 9 switch. So, in fact, I can actually generalize, I can even make it 4 here, does not matter, I can make 12 by 12. Okay, let us do it. So, number of switches in the middle stage will always be 3. Okay. So, this will be a 4 by 4. Oh, this will be all 3. So, I can connect So, this what the switch is all about. This is a reasonably non-blocking switch. So, these are 4 by 4, 3 of them. R2 here is greater than or equal to M1 or N3, both are 3 actually. So, R2 has been taken as 3. So, this is a reasonably non-blocking switch. So, let us set up some arbitrary connection and see how we will take care of the blocking. Okay. So, I will keep on setting up the connection whenever the blocking will happen. I will try to use Paul's matrix to solve it. And then we will actually look at a looping algorithm case and prove that this is nothing but exactly what I am doing here. The same algorithm will work even in that case. Okay. So, let us take up an example, map here. So, is 1 to 12 at the input, 1, 2, and I will not do it in order, I will just do random thing. So, these have to be connected to, just take some random stuff. So, that is what will be the map. So, I have just taken randomly something, and let us try to sort out, and I will do it in random order, I will set up the connections. So, let us do with 7 4 first. So, I will draw it with a different colored chalk so that you can actually see it. So, this is 1 2 3 4 5 6 7. So, 7 has to be connected to 4, and I can take arbitrary anything, I do not bother, whenever the blocking will happen, that time we will correct it. So, let us put something here, it goes 7 to 4 connection has been made. Let us take 10 to 10. So, 10 to 10, so far I have not seen blocking. 4 to 9, let me put 6 to 8, eight to 12, let me do that. Oh, through this route I cannot do it, I will do it through this route. Three to 5, so if I do not get blocking, I will create blocking later on, I have to just swap the maps actually. 11 to 3, let us do how this will be done. 12 to 11. Oh, now I cannot connect from 12 to 11, this is not, this blocked, because if I want to set up 12 to 11, I cannot use these two, these are already occupied, I want to use this one, this is already occupied. So, how to connect 12 to 11, that is a blocking. So, now let us actually draw the Paul's matrix and then rectify the problem, do the rearrangements. In fact, there will be a pair of connections you can identify, you will be able to identify which are blocked. So, you have a 4 by 4 Paul's matrix, so I will give them number 1, 2, 3 and 4, 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 and the middle stage switches I can always write them as A, B and C. Okay. So, now let us look at the connections which we have already set up, and in the end I will look into this 12 to 11 how this will be done. So, I have connected 3, look at the top one by one, 3 to 5 via A. Okay. So, 3 to 5 via A, so A has to come here. Okay. Next 4 is being connected to 9 via C, 4 is connected to 9 via C. Okay. Then 6 is connected to 8 via A, 7 is connected to 4 via B, 7 is connected to 4 via B, 8 is connected to 12 via A, then we have 10 is connected to 10 via C, 11 is connected to 3 via B, 11 is connected to 3 via B, and then I was trying to connect 12 to 11. So, 12 actually comes in this and I am trying to connect here. Okay. So, which actually means I have to make some entry here. Now, look at the condition, look at all the columns A and C, B and C. If I take the union A, B, C, all 3 of the elements have been consumed. Condition B is being satisfying here. Okay. But now how to do the rearrangements? So, let us see how we will do this before we can sort out this particular problem. So, I need to find out if condition 2 is true, condition 1 is not true, so condition 2 should be true. So, if I look in this row, I found a B which is not present in column. and correspondingly there is an A which is not present in the row. So, the pair is now A and B. So, how to sort out this issue? So, one way is I can look into this B and then make the change. I can try to find out the chain that way, or I can do it the other way around. So, maybe let us do it this way. So, if this is A, let me find out a chain here. Okay. So, once I have found out a B here, I have to now look into the column. So, now if I do any chain actually stops. So, what I have to do is I have to now simply replace this by B, this by A, this by B, and now A is free, I can use A here. So, this is a rearrangement. So, if we do the rearrangement, let us see if the connection happens or not. There is another alternative which is possible, we will also do that requires less number of rearrangements. Okay. So, what I have to do is from element 1 which is 3 to 5, this particular connection 3 to 5 which was via A has to go via B. So, 3 to 5 this particular connection which was going via A, I have to move it via B now. So, let me take it with so this connection will also be dismantled. And I have set up this connection. The one which I have dismantled was from 3rd to 2nd via B, this one. So, 3rd to 2nd actually is 7 to 4 which is this, and this is what I dismantled here. So, 7 to 4 now has to go via A. Okay. So, which actually means this one will be dismantled. So, I will be connecting 7 to 4 via A, and then we had a connection here which corresponds to 8 to 12 which has to go via B. So, 8 to 12 which I had dismantled here, it has to go via B. From here this 8 to 12, so it has to go downward now. So, this is being dismantled from upper actually one. So, this from here I have done 8 to 12, and now I can use A to set up the connection from 12 to 11. Okay. So, I can now use 12 to 11 connection done. I have done the rearrangements. Okay. I could have also done a rearrangement by actually doing a search here, only B would have been moved to A, and then I could have been putting in A here. Okay. So, let us see if that also would have worked. So, I am actually now coming back to the original configuration. So, this will be A, B, A. So, now what I have to do is I have to replace this B by, if I want to do a, instead of doing through column I would have done it this way, only one, there is chain search stops, I could have converted this to A and a B could have been put here. So, that would have mean, so I have to now reset the connections here. So, I will just set up these things again. So, 2 goes to 3 goes to 5 via A, then 7 goes to 4 via B, eight goes to 12 via A, yeah. 11 to 3. So, this is the current connection 11 to 3 is via this route. So, now I have to do the 12 to 11. So, alternative is this particular connection, this one is being dismantled, this corresponds to 11 to 3 which has to go via A. So, 11 to 3 I will just move it via A. So, once this goes, this one becomes free. Eleven to 3 via A. Okay. So, once that has been moved via A, then I can set up 12 to 11 via B. Okay. So, 12 to 11 now can be set up via B. Only one rearrangement was required and a fresh connection was set up. Okay. So, this was the more optimal scenario. So, minimum of the two has to be taken.